Okay, guys, it's 2:30, so let's get started. So for the next two or three classes, we'll be talking about something called flow, and this is a new chapter in our course. So we just left greedy algorithms, and flow is like another kind of technique to add to your collection of techniques that you have to solve solve problems, algorithm problems. And when I describe flow, it's going to be a little bit like challenging, right? There's going to be a little bit more definitions than we're used to. But then later in the next subsequent classes, we'll see that flow is like a really powerful primitive to have. Like it lets you solve a lot of problems, and it just has a lot of nice combinatorial structure that lets you design like a very nice algorithm that has a lot of cool applications. Okay, so let's get started. Okay, so the plan for today, right? We'll be talking about something called cuts, flows, and then this sort of kind of magical theorem that relates two things that seem like they're not related. Okay, so let's get started. So right, as we saw in minimum spanning tree, right, a cut is just a partition of the graph into two sets, and we just count how many edges cross those two sets. Okay, so cut is like literally like you take you put one thing on one side, the other thing the other, and how many edges go from one side to the other. Okay, so in minimum spanning trees, the edges in the graph did not have an orientation, right? They were just unweighted, or they were weighted but undirected edges. But now for flow, every edge will have an orientation. Okay, so it will look like this. Okay, so for the flow problem, right, the graph is going to be a little bit more structured. We're going to have two special nodes, okay, and they're called S and T. So S stands for source, and as we'll see later, but S is sort of like, you can imagine it's a factory or like, a giant pool of water, right? It has a bunch of stuff, and T is a target, okay? And I want to send stuff from S to T, okay? So S and T are not just arbitrary nodes in the graph. They're like special nodes that are given. And now every edge has an orientation. So it's like pointing from one node to the other. And it also has a number, okay? It's like, as you can see, right, 4, 3, 2, so on, 4, and so on. Every number is like sort of how much stuff can that edge hold, or how much stuff can you transport from one endpoint to the other endpoint, okay? So this is the first time that we've seen where sort of edges have this parameter, right, that kind of represents how much stuff that I can send from one node to the other, okay? And now we're going to be talking about cuts, okay? So previously, a cut was just a way to partition some nodes of the graph from the other nodes, okay? But now a cut is going to have a special meaning. It's a way to separate S and T, okay? So S and T, like I said, are special nodes in the graph. And a cut is it's the same thing. It's like I want to kind of put S on one side and T on the other side, okay? So that's why I call it an ST cut, all right? And now we say, okay, what is the value of the cut? This time, rather than the value of the cut being how many edges cross, we're going to have to keep track of the orientation, okay? So essentially, the value of the cut is we only count the edges that go from the S side to the T side, okay? So for instance, this edge that goes from the T side to the S side is not counted. And now the value of the cut is sort of the capacity of the edges that go from S to T, okay? So only these three edges count because they go from the S side to the T side, and this edge has value 2, 4, and 10. So the capacity of this cut, or this the cost of this cut is 16, okay? Does that make sense? Like the value of a cut, directed graph, S and T. Yeah. This? Yeah, why? So this is just the way I'm going to be defining a cut for this class, okay? So I mean, it makes sense, right? Like previously, we included all edges that go anywhere. But for this class, for the flow problem, it's going to be really important that it goes from one side to the other. Like where it starts and where it ends matters, okay? And we'll see, like, we'll see in a bit why this matters. But for now, this is just a definition, okay? The way I define an ST cut is, I put S on one side, T on the other, right? And then some vertices, I put them on one side or the other, and then I accumulate the costs of the edges that go from one side to the other, okay? From the S side to the T side. So I'm just defining that as the ST cut, okay? Any other questions, comments? ST cut, yeah. Yeah, it doesn't do anything, right? So yeah, essentially, like a cut is just a way to, like we'll see later, but it's a way to sort of break the connection between S and T. So what happens inside doesn't matter. The only thing that's interesting for this class is, or like for these 4 classes and so on, are the edges that go from S to T. Okay. Oops. What happened? Okay. All right. Any other questions? So this is just a definition. Okay. So right, like I said, I'm going to be defining a bunch of things, and then later we'll see how things are connected. Okay. All right. So so one problem that I'm interested in is called the minimum ST cut. It is the sort of the best way to break apart S and T. Okay. So like I showed you, right? This is one possible cut. Okay. This is one possible ST cut, and has value 16. Okay, because it's the sum of all the costs of the edges that go from the S side to the T side. But this is not the best cut. There's actually a much smaller cut. For instance, if I cut the graph like this, then the total cost of the edges that go from the S side to the T side is only 11. Okay. So one problem that I'm interested in is how do I find the cheapest way to cut S and T? Okay, that's called the minimum ST cut. Any questions? Okay, so why would you care about this problem? Okay, so like I defined a bunch of things. I redefined what I meant by a cut. So now this problem actually has a really cool history, and actually like this is like when I was taking algorithms, this is my favorite example of an algorithm. So in okay, this is history, right? It's not going to be on your quiz or anything, but it's pretty cool. So this problem was first studied in the 1950s, and it was studied both on the US side, kind of by these Eastern European mathematicians that left, and it was studied in Eastern Europe and and Russia, where the mathematicians stayed, right? I mean, there are many mathematicians, and so I'll first present it from the Russian side, okay, or sorry, from the side of the US. So in 1950s, right, there was a Cold War, and they were saying, okay, there was a train network, right, that starts from the Soviet Union and goes to Eastern Europe, and it's like, okay, there's a bunch of rail networks, and basically, right, what the US wanted to do was say, okay, we want to destroy the rail network as efficiently as possible, right? We want to drop, okay, I didn't add the slides, but essentially they wanted to drop bombs on certain lines, okay, such that they could disconnect the Russian side and the Eastern European side, okay. So actually, as you can see, right, like, right, this line says this is the bottleneck, and on everything, you have this number, okay? That's the capacity of that link, okay? It's like the amount of stuff that you could send from like one edge to the other edge, okay? So right in 1955s, mathematicians in the US were thinking, okay, how do I, what is the best way to break up this connection so that, right, if I start from, what's the best way to break up this connection so that the Russians cannot send stuff to Eastern Europe, okay? And that's the same thing as the min ST cut, okay? So that's the same thing as min ST cut. Like we have the source, right, that's, has a bunch of stuff. We want to get it to the target, and the min ST cut says, okay, what is the best way to separate S and T measured by like, the cost of these connections. Okay. So that's one cool history. All right. Any questions about the min SD cut? Okay, so now there's another problem, okay, that I'm gonna talk about. It's gonna be a little bit different than the min SD cut. Okay, so now we're gonna temporarily change topics, and then we'll see like how those things are actually the same. Okay, related. Now we're gonna talk about flows. Okay, so far we talked about cuts. Now we have to talk about flows, right? A flow is basically the amount of stuff that you're going to be sending from S to T. Okay, so in this class, the flow is represented by these boxes. Okay, so it's saying, right, what I'm going to do is, so what you pretend is S has like an infinite amount of stuff, as much stuff as you like, and it wants to send that to T, but it has to use these connections. Okay, and these connections have costs, right? It's saying, okay, on this edge, at most 10 units of stuff can go on it. Okay, so a flow is just a way to say, okay, here's a plan that you can follow that will send some stuff from S to T. So here, let me just trace the arrows. So it's saying, okay, S is going to send 4 units of flow. Okay, and how is it going to do that? Well, 4 is going to go here, and then like from here it's going to split up and so on. And at some point, 4 is going to end up at 2. Okay. So a flow has to satisfy the following 2 things. Okay. So first, like the amount of stuff on an edge cannot exceed its cost or the capacity of the edge. Okay, and that's a pretty natural constraint. Okay. So here, like you see, right, this edge has flow 1, and the maximum amount of stuff that can be on this edge is 2. Okay, and 1 is less than 2, so we're happy. Okay. And the other constraint that must be satisfied is besides S and T. Okay, so you can imagine S is like a factory; it's making a ton of stuff. T is like people, like they want to consume as much stuff as possible. Besides those 2 nodes, every other node has to satisfy the following, which is the amount of stuff that goes in has to be equal to the amount of stuff that leaves. Okay, all right. So, for instance, right. As you can see, like for this node, right, no stuff is going in and no stuff is coming out. Okay, it cannot be magically that like there is no flow on this edge, but somehow it had like 1 unit of flow here. Like that's not allowed. Okay, so we want stuff in is equal to stuff out for all the other nodes besides S and T. Okay, so what that means, and I'll show you in a bit, is that right whatever starts off with S that has to end up with T, right? Because in any intermediate node, the stuff in is equal to stuff out. Okay, any comments, questions? Yeah, so this is like a pretty important part, like that you understand what a flow is. So if you have any, confusion, like this is a great time to ask. Otherwise, you're going to be lost for the rest of the class. So, yeah. Okay, so let's recap. Okay, so I give you a graph. And I give you 2 nodes, right? S and T, the source and the sink. And the graph, every edge on this graph has a cost, or like the maximum amount of stuff they're allowed to send. Okay, so that's just a fundamental property of the graph. And then I say, okay, given this graph, can I actually have a plan of sending stuff from S to T? And that's called a flow. And the flow, right? So in this graph, right, this represents the cost, or like the maximum amount, and these boxes represent the flow. Okay, it's like on this edge, there's 4 units of stuff going from S to this node, and from this node, there's 1. This to this, there's 1, and this to this is 2, right? So as you can see, right, this flow satisfies that flow in is equal to flow out. Okay, like you see at that node, like I said, right, there's 4 things coming in and 4 things going out. Here, right, there's 1, 2 things coming in and 2 things going out. Okay. Does this make sense? Yeah. Yeah, so we'll see in a bit, but as long as it satisfies these properties, it's like a valid way to send stuff, right? It might not be the best way to send stuff, but as long as like things in is equal to things out, and you're not like violating the maximum number of things that can go on an edge, it's a valid flow, okay? Yeah. No, so the difference is the amount of stuff that you send on an edge can never be more than the capacity, right? So capacity, you can think like, another way to think is like, these are pipes, right? Like these are the rail networks, and this is like how much stuff can this individual link in the network can carry, right? Or you can think that these are pipes, and like how big is the pipe, right? So this pipe is like really wide. It can transport like 10 units of flow, okay, 10 units of water. Okay, so it's like, let me start from the beginning. Like this is like this is what you're given, okay? You're given a graph where every edge has this thing, and now a flow is just a way to send stuff from S to T while respecting the following constraints, okay? One constraint is like you can never send more stuff than what's on an edge, okay? So for instance, right here, for this edge, the maximum amount of stuff you can send on this edge is 4, and you're actually sending 4, okay? And the other constraint that has to be satisfied is for every other internal node, the stuff that goes in has to be equal to the stuff that goes out. You cannot magically create stuff, or you cannot magically like hide stuff, okay? So that's called a flow, okay? Any other confusion, comments? Questions? Okay. So here, so we say, okay, how do I say if a flow is good or not? Well, we say, okay, how much stuff was transported from S to T, okay? That's the value of the flow, which is, right, I send out 4 things from S, and if every internal node has the property that in equals out, then eventually they all end up at T, right? And that's the value of the flow, which is how much are you sending from S to T, okay? Of course, this makes sense. Like, we want to send as many things as, we want to maximize the amount of flow from S to T, and this is not the best way to do it, right? Like, this is just one way to do it, but this is not the, this may not be the best way. Like, this is a pretty wasteful flow, right? Because I'm not like, for instance, I could use, maybe if I go here, and I could send more stuff here, right? That I'm not doing. So this is just an example of flow, but it's not the best flow. Now this turns out to be the best flow to send stuff from S to T, okay? And what is the value of this flow? Anyone? Like how much stuff ends up at T? How many units of stuff? Yeah. Yeah. 11, yeah, exactly, right? It's like, you can just see, okay, how much stuff is ending at T is, oh, it's right there, okay. My bad, I thought. Anyways, okay, so now we study 2 problems, right? One is min cut, ST min cut, which is I want to cut some number of edges that like blocks me from sending stuff from S to T, right? It like totally disconnects S to T, and this is the best bottleneck way to do it. And now on the flip side, we studied this problem called flow, right? Or defined this problem called flow, which is kind of like the opposite problem. I want to send as much stuff from S to T as possible. Now, where does this problem come from, right? Like I was saying, right, on the west side, I guess, people were trying to figure out how to bomb rail links to disconnect one side or the other. But on the Russian side, they were saying, okay, we have a bunch of food that we want to, whatever, supplies. We want to send from one side to the other, right? Actually, for this rail network, you can see so these numbers turns out to be the flow that they're sending on these rail networks. So it's a bit hard to see. So this rail network has both flows, and and you can check the flow is never more than the maximum amount of stuff that can be on this edge. Okay. So that's kind of funny, right? Like on one side, people were studying this minimum cut problem, trying to disconnect things, and on the other side, they're studying this flow problem where they're trying to send as much stuff from one side to the other. Okay. Right. And yeah, I don't know. You can take 2 minutes to read this. It's pretty interesting. Anyways, you can read this after class. Yeah, like it all comes from this declassified document in the 1955 where they're saying, okay, yeah, actually, yeah, we're trying to bomb these real networks. But of course, like there's also these corresponding documents on the Russian side where like there are mathematicians writing papers about trying to send stuff. Okay, so it's pretty cool. And you can kind of read this. But okay, what is the moral, right? It's like one side was trying to, break things apart. The other side was trying to send stuff. Okay. Okay. So like I said, right, like in this graph, the maximum flow was 11. Okay, you can trust me. That's the best way to send stuff from S to T. But now, if we go back a little bit to a previous slide, this value 11 was also the best way to disconnect things. Okay. Okay. So let me just show these two things. Okay. So 11 was the best flow from S to T. Okay. It was okay if I want to send stuff from S to T while respecting the flow constraints, I can only send 11 units of flow. I cannot do better. Okay. And then like even before, right, without talking about flow, I said if I want to make sure S and T are disconnected, then all I have to do is I have to break these three edges, and that's the best way to do it. Because if I break these three edges, then S and T, right, there's no edges going from S to T, so I cannot send any stuff, right? There's like a cut, right? I cannot go from S to T if I break these three edges. And the value of these three edges turned out to be 11, okay? So what is cool, right? Like this 11 is the same thing as this 11, right? It's the same number. Coincidence, and like probably, as you can tell, it's not a coincidence, okay? And we'll see in a bit, but somehow these two problems are exactly the same thing, okay? The best way to disconnect turns out to be the best way to send stuff from one side to the other, okay? That's what this class is about, okay? So this is called the max flow min cut theorem, which is the max flow, which is how much the maximum amount of stuff you can send from S to T, turns out to be the same as the minimum cut separating S and T, okay? And not just for like this particular example, for the network where you have an S and T and directed edges and like cost and so on, okay? For any such graph, the max flow is equal to the min cut. Okay. So we'll actually I'll give you a proof, but but any like comments, confusion, anything that we can go back on. But yeah, this is probably like the most interesting theorem that we'll cover in this course. Well, there is one more, which is NP completeness, but we'll see that later. Yeah. Yeah, exactly, yeah. There can be multiple ways, but the value of the flow will always be the same, and it will be equal to the min cut. Any other questions? Yeah. Exactly, yeah. Yeah, exactly, yeah. So yeah, so that's the other perspective. Right? It's like one side is trying to like send as much stuff, okay? That's the flow side, and the other side is trying to find the bottleneck. And it turns out the maximum thing you can send is equal to the bottleneck. That's essentially what this is saying. Like the one way people talk about it is like, okay, like these are pipes that hold water. This is like a source of like a giant lake that's trying to flow. This is like a giant hole, right? And you say, okay, how much water is flowing from the lake to the hole? Well, it's like whatever the bottleneck is, that determines how much water can flow. Okay. Okay. So any other comments, questions? Okay. So now for the rest of the class, we'll prove that these things are the same. Okay. And the way we prove it is going to be cool. We're actually going to give you I'm going to give you a way to find the maximum flow. And actually, when we analyze the algorithm, it's going to show that that's equal to the min cut. Okay, so it's going to be it's not going to be a proof by math. It's going to be proof by like actually doing something on the graph. And okay. But first, let's prove one side of this claim, okay, which is so I want to show max flow is equal to the min cut. Actually, the thing that's a little bit not so difficult to prove is max flow can never be bigger than the min cut. Okay, so that's gonna be easier. But actually showing that it's equal is like not that easy. Okay, it's pretty non-trivial. Okay, so let's prove the first half, which is max flow can be never. The flow from S to T can never be bigger than the minimum cut. Okay. So the proof goes like this. Okay. So as one of your friends was saying, it's like the bottleneck. Okay. The bottleneck exists, and like we can never do better than the bottleneck. Okay. Of course, it's surprising that we can match the bottleneck, but first let's see one side of the inequality. Okay. So what is an ST cut, right? It's just a way to say, okay, some vertices go on the S side, some vertices go on the T side, and then we have some connections from S to T, okay, going one way. And for this cut, right, these orange edges are the value of the cut. Well, there's some stuff that has to come out of S, and here it's going to go back and forth, whatever. But then at some point, right, it has to go from one side of the cut to the other side. Right? At some point, that stuff has to cross. So whatever stuff that was released from S, right, the amount of the amount of flow, well, it's going to be bottlenecked by these orange edges, right? Because at some point, it has to go from the S side to the T side if it wants to reach T. And because it has to go from one side to the other, and the only the edges that you can take are these orange edges, right? Only these orange edges will let you cross, right? The total amount of flow that's crossing can never be more than the sum of the cost of these edges, right? Does that make sense? Okay. It's like I've demonstrated a cut. What I have demonstrated is like for any cut, the flow can never be larger than the size of the cut. And again, the reason is like at some point the flow has to go from one side to the other, and the only way you can do that is by crossing on these edges. So of course, the total cost of these edges is an upper bound on the flow. Okay. Does that make sense? So that actually that shows one side, right, which is max flow is never bigger than the minimum cut. Okay. Does that make sense? Yeah. It's the capacity values, right? So a cut is only defined by the capacity of the edges. I'm saying now I have first I look at the flow in the network, like the graph, right? And I say, okay, this is a bottleneck, cut capacity. Now I send flow through the network, and I say, okay, at some point the flow has to go from one side to the other, and it's bottlenecked by the edges that it's traveling on. It can be and that can never be more than the sum of the costs or the capacities of these edges. That's all I'm saying. Okay. So at least that shows you one side, right, which is the maximum flow can never be larger than the bottleneck cut. Okay. But showing that there is a way to send flow that matches this bottleneck is actually that's the interesting part. Okay, which we'll show in a bit. But at least this statement, is that clear? If not, please ask. Okay, that was a proof by picture. It's a good exercise to actually write things down. Okay, but I'm not gonna do that. But right, the thing I claimed is stronger, right, which is I can actually find a flow. I can actually send that amount of stuff which matches the bottleneck. Okay, and that's going to be that's not going to be proof by picture. I'm going to actually show you how to do it. Okay, and that's called the Ford-Fulkerson algorithm, right? Ford and Fulkerson, there were these two people that were studying these Soviet things in 1955. Now we have much faster ways to do this, but but this algorithm is sort of like the first algorithm, and it's pretty nice to see. Okay? And in the next class, we're going to be talking about a slightly more advanced algorithm. Okay. So now, like, I give you a graph, and that work, and in the beginning, there's no flow, right? Right. See, there's no, I don't have anything on the edges. The flow is, the flow is 0 so far. And now let's think, like, if I have something like this, how can I send more stuff from S to T? Any ideas? Like, if I just give you an empty flow to begin with, what is like one natural thing that I can at least send some stuff from S to T? Yeah. Yeah, but what do I need to do that, right? I need a path from S to T, right? I need a way to reach S to T. So that's going to be essentially the main idea. We're going to keep finding paths from S to T, and that's going to help us send more and more flow. Okay. Like I said, how do we improve our partial flow? Well, let's just try to send one unit of stuff in the beginning, right? Let's not try to send everything. Let's just send one unit of stuff. And then we're going to try to keep sending more and more stuff from S. And then at some point, right, we're going to hit the bottleneck, and then we'll be done. Okay. All right. So this is the outline of the algorithm. Initially, the flow is 0. There's, S has nothing going from S, and then we're going to slowly increase the flow by 1. Okay. That's the main idea. And now to keep track of progress, we're going to introduce this other graph. Okay. It's called G sub f. It's not like it's something that we made up. Okay. It's like it's not part of the input, right? The input is just the graph that you see. But we're going to sort of create another graph to help keep track of how the algorithm is progressing. Okay. All right. So let's just say we're in some intermediate stage of the algorithm, right? I've sent some amount of flow from S to T. And now I'm going to create this residual graph as follows. It's going to look like this. Okay, so this is a complicated object. So let's move a little bit slowly. Okay. So like I said, this graph doesn't really exist. Okay, it's just something we're going to create while we're running the algorithm. So how is this graph going to look like? It's not going to have any flow. Okay. Essentially, the point of this graph is it's going to help us figure out how to send one more unit of flow. But this graph itself doesn't have anything. Okay. But the thing that it does have are these edges. Okay. So how do I define these edges? So essentially, I look at every edge S to, from some node to some other node in the original graph, right? Initially, it has a cost, right? Capacity, and I'm sending some flow through that edge. As you can see, right, whatever is left over, right, 4 minus 3, that edge will exist in this other graph, okay, in this GF. And it's going to have cost 1. But we're also going to keep track of the fact that I send 3 units of flow on that edge by adding another edge that goes the opposite way, okay? And that I'm going to draw as like these green edges, okay? So as you can see, like, okay, right, this is some flow on this graph, and it ends up, we can take this and construct this other graph, okay? And I haven't told you like why we do that, but as we'll see, like this graph is going to help, something about this graph is going to help us say, oh, can I actually make this flow a little bit better, okay? So that's the point of this graph. All right, so that's the first step, okay? Initially, right, in the very first step, there is no flow, right? We start with the empty flow, so this graph just looks like the original graph, okay? But as the flow, like, as we keep adding more and more flow, as we keep sending more and more stuff from S to T, this graph is going to change a lot, okay? So that's the first step. We're going to start with the 0 flow, and we're going to maintain this other graph. All right? And like I said, these blue edges are going to keep track of how much stuff can I still send on that edge, okay? How much stuff is left to send. And the green edges is going to keep track of how much amount of stuff have I already sent on that edge, okay? And now I have to define this thing called an augmenting path, okay? So I'll tell you what an augmenting path is, but essentially, as your friend was saying, right, like the way we improve the flow is we find a path from S to T. But like, as we add more and more stuff, some paths will get destroyed, right? Because some of the edges will become totally like saturated, right? But we still need to somehow go from S to T. And the augmenting path, which I'll define shortly, is going to help us say, OK, that's one more path that I actually haven't sent stuff on. And that's one more path that I can use to increase the flow, OK? So what is an augmenting path? Essentially, it's a path in this other graph now from S to T, OK? Just like it's not the shortest path, like I don't care. I just want to be able to reach from S to T, OK? Like I said, right? And the point is on this graph, I can go from, on this graph, I can use both the blue edges and the green edges, OK? So for instance, this is one path on this graph, OK? All right? So let me backtrack, right? There is on this graph, right, which comes from this flow, right? OK? Well, what I do is I say, oh, look, there is a path that's from S to T, right? I go on this one edge, 5 edge, and 1 edge. That's a path. And this path actually corresponds to a way to improve the flow, right? Because if I follow these 3 edges, look, it's saying, OK, I can actually send one more unit of flow here, one more unit of flow here, one more unit of flow here, OK? So that's an the augmenting path. It's just a path from S to T in this graph, G sub f, OK? And the point is that if there is a path, any path from S to T, I can either use blue edges or green edges, then it's possible to increase the flow in the actual graph I care about by at least 1. Okay? If all the, let's say all the capacities are the integers for now. Okay? At least does the statement make sense? I'll show you a proof. But at least it's like, if you don't understand what an augmenting path is, this is a great place to ask. Right? So where does the name come from? Like augmenting path. Well, it's augmenting because I'm improving things. Okay, that's where the name comes from. Yeah. Yeah, exactly. Yeah, exactly. That's the point, right? It's like we want to still find paths from S to C that has something left, right? Some capacity left, because right, if we ever find a path that has, all the edges have capacity left, then that's one way to increase the flow, right? I can just send stuff. But then how do I find these paths? It turns out it's going to be found in this other graph. Okay, so we'll see that in a bit. But exactly, that's what an augmenting path is. It's just one more path to increase flow on. Okay. So the claim is that if we can find an augmenting path, which is a path in this graph, G sub f, from S to T, then I can increase the flow, okay, by augmenting on the path. What that means is I can increase the flow because I found a path that still has, every edge has some capacity left. So of course, if I send stuff on the path, I go from S to T, right? I can send more stuff. So so one case is the following, right? If every edge on the path from S to T is only traveling on the blue edges, right? The edges that exist, then that actually corresponds to a path in the graph, right? Like I said, right? If I take this blue path, this blue edge, and this blue edge, then it actually corresponds to a path in the graph where I can just increase all the flow, okay? Right? And the reason is like these blue edges just keep track of how much stuff on the edges that I can still send. Okay, it's like the capacity that's left over on these edges is kept tracked by the blue edges, right? So if I find a path that's all blue edges, then that's great. Then I can send stuff on the blue edges. Okay. Does that make sense? So so the first step is like if I find only blue edge paths, then I'm very happy. Okay. Questions? Okay. Now the interesting case is actually, right, in this graph, I told you that I'm happy with paths that use any edge, okay? If it uses a green edge as well, I'm also happy. Now that's going to be a little bit weird, right? Because the green edge is something that like where I already, this green edge just means that I've sent 1 unit of flow here, okay? But it turns out that if I also send things on green edges, it may cancel some stuff, but overall it will increase the flow, okay? So that's the interesting case. Okay, so let's say, okay, so we've changed the graph a bit, right? Let's say the graph looks like this. This is the original graph, right, with some flow values and some cost, right? Capacity values, flow values, right? This corresponds to a graph G sub f, right, where the green edges are the flows, right? So this edge has no corresponding green edge, right, because there's no flow on it. But now you notice the following, okay? There is a path from S to T on this graph that takes a green edge, okay? Like, right, it takes this blue edge, this green edge, and this blue edge. What does this green edge correspond to, right? This green edge corresponds to an edge in the graph that already has some flow, okay? So before I show you the technical details, the main idea is that sometimes it's okay to cancel flow on some edges, as long as overall I can send more stuff from S to T, okay? So what's going to happen is, right, I'm going to send some flow from S to T using some edges, and I'll have to cancel some stuff. Like I have to take back some stuff. As long as I can, the only thing I care about is sending more stuff from S to T, okay? So let's do it a little bit, one step at a time. So let's say there is a path from S to T that uses one of these green edges, okay? What that means is, okay, then the path that on this graph looks a little bit weird, right? It's like saying, oh, I go on this edge, but then I kind of want to go on this edge, I guess, and then this edge. I mean, I can't just like increase flow on this edge, this path, right? First of all, if I increase flow here, let's say 1 to 2 to 2, then this is not going to satisfy conservation, right? It's not going to be that like where did this 2 come from, right? That's a little bit weird. So instead, what's going to happen is if I, on this graph, if I go through a green edge, what that means is I'm canceling the flow on this edge, okay? All right? Does that make sense? So I'll show you why this still increases some stuff, like why this increases the total amount of flow. But essentially, the main point is, right, if I take a blue edge, then I'm adding flow. If I take a green edge, then I'm actually canceling flow. And the intuitive reason why this still helps you is you're still pumping more stuff from S to T, okay? Like this path is telling you, right? It's telling you how to send more stuff from S to T. It's just that in the intermediate steps, you may be canceling some stuff, okay? But at the end of the day, as long as we satisfy that flow in equals flow out, and we're sending more stuff from S, then they has to end up at T. So that means like you're still increasing the flow by 1, okay? Okay, so yeah, so let's see this the example one more time, okay? So I started with this flow, right? Maybe it's optimal, maybe it's not. I want to make it better. The next thing I do, like I said, right, the forward focus algorithm, it finds a path from S to T in this graph, G sub f. Oh no, it's taking a green edge. What that means is on the actual graph that I have, the blue edges get a +1, and the green edges get a -1, okay? Okay, so I still need to explain like why this is a valid thing to do, but at least like what we did, does that make sense? Like on the green edges we canceled the flow, on the blue edges we added flow. Okay. Questions? Yeah. No, just subtract by 1, right? Subtract 1. Yeah. So the intuition is like, going from here, right? So the flow here was 2, right? There's two units of stuff going to T. So what I do is I find a path from S to T in this graph. The path says, oh, go on this blue edge, green edge, blue edge. And the hope is that I can send 1 more unit of flow, okay? And what do, right? I increase this by 2. And then I want to go down here, right? But I can't. The orientation of the edge is this way. So intuitively, I'm going down this edge by canceling the flow. And then I can send one stuff, okay? So then it ends up looking like this, right? Now the flow is 3. And let's check, right? Flow in, is flow in the same thing as flow out? Look, there's 2 stuff going here, 2 stuff going out. You know, 1 stuff going here, 1 stuff going out. So flow in is still equal to flow out, okay? But look, I have increased the amount of flow by 1, okay? So let's go back to this case, okay, which is much simpler to understand. Essentially, the point is like there is not too much. This case is essentially the same as the other case. It's just a little bit weirder to think about, like we're canceling stuff. But intuitively, it's still helping us find paths from S to T where we can send flow. Okay. All right. So now let's see why this is valid to do. Okay. So here's, just to put everything in one place, right? Here before, right? Everything was in is the same thing as out. The flow was 2, right? The graph, the residual graph looked like this. Then I found this, weird path from S to T, and then I augment on that path, right? But augmenting on this edge, right? I can't really go back on this edge. This edge goes one way. So intuitively, what I'm doing is I'm canceling flow, and that allows me to move backwards. Okay. All right. Yeah.
So you can cancel the flow to make it 0.
Yeah.
Is it possible to reverse the flow so you're almost down?
Intuitively, that's what these green edges are helping you do. Essentially, every time you send a flow on an edge, you have the option of canceling, right? So that means intuitively you can go backwards on that edge now. Okay, so initially, right, the pipe flows one way, right? Like pipe is pointing. I can't break that, and I send some stuff on it, right? But because I send some stuff, I have the option to take it back, and intuitively that option is allowing me to go backwards on that edge. Okay, we'll prove this in a bit, but at least step by step, like what happened, does that make sense? Like you may not understand why it happened, like why it works, but at least like the steps that I took. Does that make sense? So all I did was find any path from S to T, and then I augment on the path. Okay, blue edges means I add stuff, green edges means I take away stuff. Okay. Yeah. So the thing that we have to check is when we cancel flow, it's still a valid flow. Okay, that's the only thing that's a little bit difficult to check, or not so obvious, right? Like we cancel stuff. Why is it still a valid flow? And the main intuitive idea is all we have to check is that stuff in is the same as stuff out all the time. As long as that's true, then it's still a valid flow. Okay? And as long as that's true, we've made progress because at the end of the day, right, I send more stuff from S. It has to end up somewhere. I check that flow in equals flow out for all the nodes, so it must end up at T. Okay? That's essentially what we're doing. So let's check that flow conservation is still satisfied, okay, when we cancel stuff. So let's say initially the flow looks like this. I haven't drawn the residual graph, but let's say, right, like the next path I find ends up taking this, it ends up taking this, backward edge and the forward edge, okay? Well, then I'm canceling flow and I'm adding flow, right? So you can think what's intuitively happening is I'm sort of like redirecting flow from one edge to the other edge. That's essentially what canceling is doing, right? Because canceling means I'm finding a path, but I still have to move forward, right? That means I'm redirecting the flow to another edge, okay? So then it ends up being like this. The first edge goes away because I canceled on it, but then I added something on the second edge, okay? Let's check the other case. Okay, let's say I cancel on this edge and I cancel on this edge. Well, then these two edges disappear, right? So flow in is still the same as flow out, okay? And you can check this is true for all the nodes. Even when I do this, even when I go on these green edges, I will always maintain the fact that flow in is equal to flow out, but I'll increase the amount of stuff that I send from S. So if flow in is equal to flow out, and I've increased the amount of stuff that I send from S, then it must end up at T, okay? So that's the proof, all right? So, I mean, that's the entire proof, right? You just have to check that conservation is satisfied. Okay. Okay, so any comments? Okay, so all right, so more, in more detail, this is the augment path operation, right? I find some path in the residual graph, right? It may take on the blue edges, which have some amount of, capacity left to send, but this path may also go on green edges. So essentially, what I do is I find the lowest weight on the path, and that's the amount of flow that I can send, okay, on this path. Essentially, that's the bottleneck on the path, right? That the value that's the smallest. If all the edges were blue, right, then it's pretty obvious, but it still turns out to be true, okay? And then the flow turns to this, right? Like I find this path, I say, okay, oh look, this path allows me to send 2 more units of flow, and then I do that, right? So now, now it ends up being like this, right? It updates, okay? And that's f prime, right? Does this make sense? So the entire Ford-Ferguson algorithm is the following, right? I start with an empty graph. I find a way to connect S to T. I send flow on that edge. Then it's going to create all these like green edges, blue edges. Then I find a path from S to T using blue or green edges. And then I say, okay, I look at the minimum weight edge on this path, and that's the amount of flow that I can that's the amount of flow I can use that path for, okay? Questions? Yeah. Yeah. Yeah, so sorry, this is just like a bigger, I'm not showing them bigger graph. I'm just showing like if this was the path found, how would this path change? But yeah. Yeah. So, yeah, so yeah, I'm only showing like the local change. Yeah. But that's true. Like you have to check that flow in is equal to flow out at every node. But I'm just showing like on this specific path, how do things look like, right? Like there could be other edges coming in from this node that I didn't draw, for instance. Okay. All right. So this is the entire algorithm in all its glory, right? I start with the all zero flow. This G sub f graph is just the G graph in the beginning. There are no green edges. While I can go from S to T in this G sub f graph, I say, okay, I find a path from S to T. It may go on blue edges, green edges, whatever, I don't care. I look at the minimum weight, minimum capacity on that edge, on that path, and that's the amount of flow that I can still use that path for, and then I keep going until I can't, okay? Okay, so you can see there's a condition, right, while T is reachable from S. And then at some point, as we'll see, I mean, it's not even clear that it finishes, okay, from the way I wrote it, but at some point we'll see, like, at some point, there's no way to go from S to T in G sub f, and that's the point that we know that we're done, okay? Questions? Yeah. Yeah, so that makes sense, right? Like we want to choose paths that can help us send more stuff, right? That's going to be the next class. But for this class, just any path will, for this particular algorithm, you pick any path that you want. Essentially, the reason is, right, any path tells you how to improve the flow a little bit, so you're happy with it, okay? But yeah, later on, we'll see how to pick paths in an even better way, so the algorithm is faster, makes more progress. Questions? Yeah.
Is it possible that the S and the T vertices, like, they're not so far apart, they're closer together? It has to get integrated and maybe in the direction. How would you
Yeah, we'll see. We'll see in the proof. Okay. Yeah. So the proof will end up happening is like in the original graph we care about, it's building a flow, but it turns out in the residual graph, it's building a cut. And at some point, they'll both be like matching, and then that will prove max flow equals min cut in a very cool way that we'll see. Okay. But yeah, so just to kind of recap what happened, right? This is just a way to send stuff from S to T, and it's a greedy algorithm, right? I'm just saying, at least is there some path that I can still use to send more stuff? If so, I find it and I send stuff on that path. That's all that's happening, okay? Except you have to, except there's a little bit of caveat, right? Or like a little bit of clever things happening where I'm canceling stuff I've already sent to even send more stuff, okay? All right, so now let's finally see an example, okay? In full detail, okay? So this is the beginning graph, right? And then the 0 is just because I haven't sent any flow yet, okay? And the 10 means like, I can only send 10 units of stuff at most on this edge, right? So every edge has this value and also a flow value, okay? And so the G sub f graph just looks like G, right? There's no flow, so there's no green edges, okay? And then the first step is I find a path from S to T. Say, oh, okay, this is a nice path, right? Oh, the smallest weight edge on this path is a 4, so I can send 4 units of flow here, okay? So then I do that, right? Like you can see, these three things get updated, right? I send 4 units of flow. But now, right, these edges go backwards, right? They become green edges, okay? And then I say, okay, now I try to find another path. Okay, look, there's one more path. There's also 4, right? So I increment by 4. And then, like, then these edges, they go backwards, right? So this edge, right? Oops, did this not update? Right, oh yeah, right? So it had capacity 10. I send 4, so there's a green edge going the other way, and there's a 6 going the, going the original way, okay? And now I keep doing this, okay? Look, there's, oops, I went backwards. Look, there's a path here. Okay, now this is a complicated path, okay? Look, because it's going on a blue edge, and a green edge, and then blue edges. So what it's intuitively doing is it's canceling the flow on that edge and like sort of redirecting it somewhere else, okay? Because, right, flow in always equals flow out, it can never disappear, okay? Essentially what's happening is like when you go back on the green edges, you're sort of like redirecting the flow to another part, okay? So here, this is a valid, let me go one step back, right? So look, see this 1, this 1, this 4, this 3, and 4, that's a valid path from S to T. And then I augment on this path. The smallest weight edge on this path is a 2, right? And look how these, oops, I went backwards, right? See, it started with the 0, and then I can add 2 more flow, okay? So far that's 10, right? And then I say, okay, look, there's even a more complicated path from S to T. And there I can add 1, right? Because 1 is the bottleneck here. And then I add 1, and then, okay. Right? You can see, like, in these intermediate steps, I'm actually, I'm going back on the green edges, so I'm removing flow at some point, right? When I go back, I'm saying I'm, the flow that was already going this way, I'm canceling it, okay? Essentially what's happening. But like if that didn't make sense, then you can just think, okay, I just find a path from S to T, and then I do some operation, okay? Okay, now you say, okay, when do you know that you're done? Look, turns out, right, after some point, there's no path from S to T, right? There are some blue edges, green edges, but like you can quickly check, right? There's no way to go from S to T now. Like, okay, maybe I go here, 5, maybe a 2, but then I get stuck, right? I can't go to T. And you can check, okay? There's no way to go from S to T anymore. And that's when you know that you're done. And look, right? The flow here is 4 plus 4 plus 3, which is 11, okay? Did this walkthrough make sense, like how these numbers were updated? Okay, yeah. Well, you can just use BFS or DFS, right? It's just a graph. You want to check if things are connected, right? You just, let's say you run BFS from S, and then in O of M time, right? You explore this connected component, and if a T is not there, then you're done, right? Then you know they're disconnected, right? BFS helps you check if things are connected, right? No. Any path is fine, right? Like that's the whole discussion, right? Like any path you find on this G sub f graph is actually a valid way to increase flow. So any path that I find, so I'm allowed to use blue edges, green edges, combination, anything. It's just that, yeah, it's just at some point I can't use any edge, any combination of edges to go from S to T. And the way I check that is I just use BFS or DFS, okay? Yeah. Yeah. Questions? Okay. All right, so now we need to prove why it works, okay? Like just because there isn't a path anymore in this graph G sub f, why does that imply that I can't improve the flow by 1, okay? So then that's what we're going to show, right? Somehow, when at that point, when S and T become disconnected, that's when you found the maximum flow, okay? All right. And this is like the non-trivial part of the proof, okay? Like the easy part was to show that the max flow is always upper bounded by the min cut. Now we're going to show the other thing, okay? All right. Okay, so this proof is going to be a few steps. So before we dive in, like, does everyone understand, what just happened? Like, if not, this is a great place to ask. And I'm happy to go back and, re-explain things. Yeah. Yeah. If not, like, the proof may not make sense if you don't understand what happened. Okay. So we want to show that, right? Like, when do we stop? When there is no augmenting path. And we want to show at that moment, we've actually found the max flow, okay? So what that essentially means, okay, I'll tell you the high-level idea. High-level idea is we want to demonstrate a cut in the graph where our flow matches the cut, okay? Where our flow is at least as large as the value of the cut. And that's useful because we know the flow is smaller than the minimum cut. We've demonstrated a cut where the flow is larger. So actually, we have min cut on one side and min cut on the other side, so everything is the same in the middle, okay? That's the main idea. So essentially the point is I have to demonstrate a cut where the flow is large, okay? Where that sort of, that proves to us that the flow value is large, okay? So what is the cut? What I do is the step that I'm done in for Fulgerson, right, the graph G sub f, I look at all the vertices that you can go from S, and all the vertices that you cannot go from S, okay? And note that like T is on this side, right? Like I cannot reach T from S, right? So that's the condition that I stopped, okay? And now the main idea is if I consider, and I'll give you more detail in a bit, but kind of the main idea is if I consider that cut, okay? The cut is defined by the things that are that I can go from S to things that I cannot go from S, okay? But now I look at the cut in the original graph, okay? This graph, G sub f, is just helping me figure out what a good cut is. But of course, I have to look at the original graph, right? This is just something we created in our heads, okay? But the original graph is what we care about. Then that cut is going to tell me that the flow value is large, okay? That's the main idea. All right. Okay, so this essentially I'm going to draw you just one picture, and then that's going to be the proof. Okay. So there is a cut, right? S and T, right? I put all the S vertices on this side, and some vertices on this side, and there's, of course, right, in the original graph, there's some edges that go this way, and maybe there's some edges that go that way, okay? First, I want to prove that all the edges that will go from S to T are actually saturated with flow. There's no more flow that I can push on those edges. Why is that? What if there's some capacity left on these edges? What does the G sub f graph look like? Okay. Yeah. Yeah, so that's the main idea. Yeah, exactly, right? If there is some capacity left on this edge, let's say, then I can reach more vertices from S, right? So how do I define this side, right? This side was all the vertices that were reachable from S in this graph G sub f. If there is some capacity left on this edge, then there will be a blue edge on this graph G sub f, and that will allow me to reach one more vertex, right? That's not allowed, right? Because this is, by definition, all the vertices that I can reach from S in G sub f, okay? So there's all the edges that go from S to T are fully saturated. That proves that, okay? All right? And you can kind of see here, right? So here the cut turns out to be like everything, and then T's on one side, and the point is all the edges that go from here to here end up being fully saturated, right? And again, right, you can see, right, if this edge was not fully saturated with flow, then there would be a blue edge in this G sub f graph. And that means, right, there's still a way to go from S to T, okay? Because by definition, this side was all the vertices that I can go from S in G sub f, okay? So that's why there are no edges in the original graph now that are, that still have some capacity left. They all have been saturated, okay? That's the first part of the proof. Like I said, otherwise you can reach more things, and that's not allowed, right? Because by definition, this is all the things that you could ever hope to reach. And now the second part is, well, in the original graph, actually, it turns out that all the edges that go from T to S, they have no flow. I actually did not put any amount of flow on those edges. Why is that? So it's the same argument as before. If I put any amount of flow, then in the G sub f graph, they would become green edges, and they would point the other way. That means this is not the set of reachable vertices. I could reach one more vertex, okay? Okay. So it's basically like using the properties of like why did the algorithm stop to argue some mathematical structure, okay? So that's the main idea. Okay, otherwise, the flipped edges in the original graph, I can reach one more vertex. Okay. So essentially, what we did was I gave you a cut, right? I said, okay, in that cut, go from one side to the other. All the edges going from one side, S to T, are fully saturated. None of the flow is coming back, right? There are no flow on the edges going backwards. So the flow that I'm sending from S to T is at least as large as the size of that cut. Because every edge going from S to T is fully saturated, right? So you can see, as in this example, right, all the edges from this side of the cut to this side of the cut are fully saturated. So the value of the flow is at least as large as the size of the cut, okay? And again, like, you can say, okay, what if at some point the flow goes back, right? Well, if the flow went back, then somehow these edges would have had flow, right? But I told you, I just proved, these edges have zero flow on them. So just to recap, right? I have some flow here, it's going to T, and like all these edges are fully saturated, and none of these edges have any flow. So what that proves is the value of the flow that I found is exactly equal to the size of this cut. This specific cut is at least as big as the minimum cut, right? Because minimum cut is the smallest cut. But then the very beginning thing was that minimum cut is larger than max flow, right? But this flow that I found cannot be bigger than the maximum flow. So what that means is the flow that I found is equal to the max flow, okay? Right? Like, look, this max flow is on this side and on the other side, right? Max flow is at least as large as value of the flow that I found, okay? So somehow it's this like sandwiching thing where I'm using the same quantity to say, okay, the thing in the middle, they're all the same, okay? All right. So the final conclusion is when the algorithm stops, it's found the maximum flow. And along the way, we prove that max flow is equal to min cut, right? Because, right, max flow is on this side, max flow is on this side, so this must be all the same. But look, min cut is somewhere in the middle. Okay? So everything is equal, and that's why max flow is equal to min cut. Okay. Let me see what's next. Okay. Questions? Max flow, min cut. It's not, it doesn't work the other way, okay? Min flow is not max cut, so don't get confused. All right. Yeah, so the cool thing is, right, these two sides are actually trying to solve the same problem, but in slightly different ways, okay? One was trying to find the min cut, the other was trying to find the max flow. Lo and behold, they were actually trying to find the same quantity, okay? That's cool. And like you can say, and again, right, the Ford-Fulkerson algorithm can help you find the max flow and the min cut, okay? How long does this take, okay? Well, it can actually take, that's the one bad thing about Fulkerson, it can take a long time, okay? So here is one example, okay? So all the costs or the capacities are really big, let's say C, initially there's no flow, but this edge has, capacity 1. If you run if you run this algorithm over again, you'll see that the flow only increases by 1 every time. Okay, but the max flow is clearly 2C, right? I can send C here and C here. If it only increases by 1 every time, then it's going to take a really long time to finish. Okay. So what is the total running time? Well, every step we have to find is our S and T connected. That's a BFS or a DFS step that takes O of M time. And how many rounds am I going to do? Okay. Any thoughts? So I know that, let's say all the capacities are integer numbers. Okay. So I know the flow is only at least increasing by 1 every time, right? How many rounds is this going to take in the worst case? And I just showed you an example. Okay. Yeah.
I guess so. An example is 2C, and we're doing one increasing by each time. So 2C, or I guess in that case that'd be the max flow.
Yeah. Exactly. Right. Yeah. Yep. Exactly. When we update flows, all we're guaranteed is the flow will increase by at least 1. Okay. We're not guaranteed anything more than that. And actually, there's an example where the flow will only increase by 1. If we start with 0 and it increases by 1, well, the number of steps it takes is the total size of the flow, right? Which is, let's say, big F. So the running time for Ferguson is M times F. Is this a polynomial time algorithm? Yeah. So it's not a polynomial time. The reason is the running time depends on the size of the numbers, right? It's that's a really weird thing because the numbers are encoded in binary. Okay. That means, right? It's like saying if I have a number 1,000, or let's say 2 to the 10, right? That number of steps it takes is 1,024, but the size of the input is only 10 bits. Okay. So it's actually this thing called pseudo polynomial running time. But the point is it's a very slow algorithm because the bigger the number I give you, the slower it takes, which is a really weird behavior, right? In some sense, the numbers shouldn't matter, right? Okay. So in the homework, we're going to see that if I give you real numbers, and I run the forward focus algorithm, it will not work. It will actually not give you the max flow in any finite number of steps. Okay. Okay. So we'll see it in the homework. But yeah, next time we're going to talk about a different algorithm. Right here, it has no F running time, right? No F dependency, right? It's just a pure combinatorial algorithm. No matter what values I give you, it's always going to give you the max flow in n m squared time. Okay, so that's next time. And the main idea there is, right? Here we were just happy to find flow on one path, on any path, right? So that's why we could only guarantee the flow would increase by 1. If we have real numbers, the flow can increase by a very, very small amount, so they will never converge. So that's why we need to pick the paths in a slightly smarter way. So the next algorithm we talk about is a much more clever way to pick these augmenting paths that will always make progress, no matter what the numbers are and so on, and it will run in time nm squared. Okay, so that's next time. Okay, all right, that's it. See you on Thursday.